Ready whenever. Welcome to my talk, Still Exploiting TCP Timestamps. The still is important in the title because we're going to look at a few things that are history related. But first, about me, the most important, of course. I work as a security consultant and researcher in Zurich, Switzerland, at a company called Skip AG. We are doing penetration testing and consulting in the area of IT security. And you can find me on Twitter. If during the talk I'm talking about timestamps and I'm not specifying which kind of timestamps because there's kind of a lot of timestamps, then I'm always talking about TCP timestamps. Also, just for those that are really, really exact, I'm using IP instead of IP address in my slides just to shorten it a little bit. So, what we're going to talk about today is generally what are TCP timestamps, how do they work, where do they come from, what were they designed for. Then we're going to look at a history of exploitation and failed remediation, that's the still part. And then we're going to have some more fun with TCP timestamps, which are the attacks that I've newly created. So that's then just the exploiting TCP timestamps part. And if we could look in the end for ideas of how to solve the issues presented, that would be great. So first, TCP timestamps. They were introduced in 1992. They are described in the RFC 1323, which even if you don't like reading RFCs, this is a really easy read. It's great. They were introduced as an extension to the original TCP stack to provide PAWS and RTTM. PAWS stands for Protection Against Wrapped Sequence Numbers. So in each TCP packet, there's a sequence number. It's increasing continuously. And the number is fairly small. And when it was designed, it wasn't intended for that fast traffic that we have nowadays. And so they wrap. That means once it hits the maximum number, it jumps down to 0 and starts all over again. And that creates problems with the packet assembly. So timestamps are to prevent that. And RTTM stands for round trip time measurement, which is so you know how long a packet takes back and forth, and you get the right sending range so you don't create packet jams and stuff. Timestamps themselves, they are a constant, strictly monotonous increasing number, basically. So it's like a clock, but it doesn't stop at 24. But it just keeps going and going and going. But it does start at 0 in all systems nowadays, more or less, I think. Under Linux, they're implemented through jiffies, for those that know their Linux kernel. This is how they look like. The first two fields are not that interesting. Does the laser work? No, the laser doesn't work. So the third field is the TCP timestamp value. When you send a SYN packet and you send a TCP timestamp in it, you put your own timestamp in that TCP value field. If somebody answers then, he will put your timestamp in the TCP timestamp echo reply field and will put his own timestamp into the timestamp value field. And this is how difficult it is to get the TCP timestamp from a different machine. You just send a SYN packet, say, here's my timestamp, what's yours? And they'll go like, here's my timestamp. So if you're wondering how that works, this is how easy it is. And I want to look at the first attack. Maybe it's the most known one. It's been around since 2001. It's uptime calculation. So how does that work? Just to specify, timestamps are not equal to uptime. Timestamps, though, multiple ones, can be used to interfere the frequency in which it is increased. So it's not specified in the RFC how fast they have to increase. So there's some with 100 milliseconds, there's some with 500 milliseconds. So it's somewhere in the millisecond range, but it's different from operating system to operating system. But from these multiple timestamps, we can get the frequency, and the frequency together with a timestamp gives us the uptime. And the uptime is related to the patch level. at least on the systems that need to reboot, because we start at 0. So now we know which patches are installed, which is really handy. How could we remediate this? So the one way to remediate this, and that always works, is to disable timestamps altogether. But if you disable timestamps, you lose pause, you lose an improved RTTM. So basically, you lose all the functionality that it was introduced for in the first place. So we'll just call it a bad idea and not put that on every slide when there's remediation. It works for every attack I present. We could randomize the timestamps at boot time. So that's the first thought. But there's a couple of problems with it. For one, there is not a lot of entropy around when you boot a computer. So random is not really that random after all. And if you look at the uptime calculation, of course, if you just look once, and then there's a randomized start, you miss it. But if you just keep probing the same server over and over again, eventually it will drop. And we know that's the time when it just started again, because it only is going up, the timestamp. So that doesn't really help. Didn't stop Microsoft from doing it for a few versions. By now they have gone back to 0 at boot time. Then we could start each new TCP connection with 0, but then pause won't work. Like, well, how should it detect if this is new or old if we do it every new TCP connection? Then we could have a timestamp per IP. So we start 1 at 0, and you're connecting, and then we're like, this is our start time. But here also it's just a matter of time, really, to figure it out, because here as well, eventually it will drop. To be fair, though, this solution was proposed not really originally to defend against uptime calculation, but it was introduced in a paper that was trying to handle sequence number attacks, TCP sequence number attacks. And then another paper said, you know, we should use this for TCP timestamp uptime calculation. But it doesn't work. So then you have another problem with this is it might break the SYN flood protection under Linux, because TCP timestamps are used as part of the heuristic to determine if a SYN flood is going on. And then another option we would have is we could use a timestamp for each IP, which I've seen implemented. I don't know what kind of base system that was. I suppose it was not a Linux, because that would pose problems, or they've taken it out of the kernel, that part of the heuristic. But that one works against uptime calculation, but I've seen it in penetration tests that I've performed maybe 3 times, maybe 4. So basically, in 2015, more than a decade later, this is still possible. This has not been fixed. That's for disclosure timelines, that's quite a bad line. Then, in 2005, there was a paper that discussed host identification. And instead of showing you a paper in words, I've tried to depict it. Basically, you can see if an attacker is attacking, and you can't read it, but it's www.example.org and imap.example.org. Those are 2 different servers. But because they are running on the same server, they share the same timestamp, because the timestamp is in the TCP stack, so each service has the same timestamp. So outside, he'll see, okay, those have the same timestamp. They're actually the same machine. So if I want to pawn HTTP, like www.example.org, and I can't, but I can pawn imap.example.org, I will still have pawned the same machine. So that's kind of a handy one. Possible remediation. So there we have randomizing zeroing timestamps, not at boot time, but generally. So one is, of course, you lose the functionality. So what's the point? There's another problem with this solution, and that is port recycling. To recycle ports, you check if the ISN, the initial sequence number, or the TCP timestamp is higher. And on most systems nowadays, the ISN is randomized already. So if you would randomize the timestamp in addition, you would maybe get problems with port recycling, and it could be that you use up all ports and you create a network DOS this way. So don't implement this version. Then we could use a different counter for each connection and initialize it with 0. Then we still lose the functionality of pause. And above, but we could use a randomized start, and we still have the problem of pause. So those are all no solutions we can use. So in 2015, 10 years later, it's still possible. So let's just simply assume for the moment we fixed these problems, where there's no good solutions for it, though. Are we done? No, we're not. Else I wouldn't ask this question. Each clock has, due to physical properties like heat and fabrication, a slight imperfection. And that imperfection makes it that we can identify hosts in multiple ways. We can use this in multiple ways, and I'm going to show you how. If I'm talking about clock skew, the clock skew is that imperfection in each clock due to heat or other physical properties. So again, 2005, we've got host identification. But this time, it's possible, even if the solution for the timestamp would have been implemented, as long as you have a timestamp. Multiple IPs virtually hosted on one virtually hosted don't share the same timestamp. They're just on the same because they have different operating systems, but the same hardware. So with clock skew, that's actually not a problem anymore, because the clock skew is due to the hardware, not to the software. So you can have multiple virtual machines, and you can detect that if they're all running on the same host, which some people have used in the realm of HoneyNet discovery. So if you look for HoneyNet security papers, you will find some of the stuff there. And till now, we've always talked about attacking servers, but now, actually, with clock skew, it becomes interesting because we can start to track users. So we have a completely different target. Tracking users by, again, identifying what their clock skew is. That clock skew is such a good identifier that the machine, depending on which, no matter what network is basically on, you can measure the clock skew, and you'll be like, oh, this is that laptop. And that is interesting, of course, especially when you think about Tor. So in the Tor network, for those that ask themselves, there's TCP timestamps are disabled for, amongst other things, for that reason. And Tails, I hope you all know Tails, disables timestamps completely. Because if you don't, it's still not safe with Tor, because you could track the user's connections up to the entry point of the Tor network, and then also when he comes back out. So you could still identify a user. So if you use Tor, make sure you disable your timestamps. Under Linux, it's really easy. So remediation. We could reduce the device's clock skew. That's a very simple thing to say and a very difficult thing to do. We'll look at ways in the next remediation slide section. We could mask clock skew, so that's basically we're just hiding it, we're kind of obfuscating it by multiplying timestamps with a random value. And we know it has to be constant, so that breaks the RFC. We could use mod skew mask. That was, I don't know if it was a PhD thesis or a paper of a PhD candidate, to mask a clock skew with a constant. So then we don't break the RFC, but it's actually pretty useless because that won't do anything to it. So if you do an ls mod in your Linux, you will not find mod skew mask in there. We could encrypt timestamps. Great idea. Breaks the RFC. We could have a table mapping between random 32-bit values and an internal representation of real timestamps, and it breaks, again, the RFC. Why am I telling you all these solutions that don't work? These are solutions that have been suggested and proposed in mainly academic papers for these problems. And just to show you that they're thinking about these problems and they're not coming up with anything useful. Often, even in the papers, they're like saying, and we know it's not going to work. So, yeah. 10 years later, still possible. So in 2005, there's another fun attack. I called it network layout information gathering. And what we have is basically this scenario. We have two servers. They each have services. These services are going through a firewall. The firewall maps it to one external IP address, and that's visible from the internet. Now, if you measure the clock skew of each service, you will be able to identify which service belongs to which host, because the clock skew is different. So that was actually kind of nice. Remediation, basically the same as for host identification. None of them work. So, again, 10 years later, network layout information gathering is still possible. 2006, there was a paper it's called Hot or Not, Revealing Hidden Services. And what it basically did is the following. We're an attacker, and we want to know if a certain IP that is in the publicly available is the same as a hidden service. How can we check if it's the same? So what we do is we create a lot of traffic. No, First, we measure the clock skew of the publicly available one. Because, you remember, through Tor, there is no timestamp. So we measure the clock skew of the TCP timestamp clock through the public interface. Then we create lots and lots of traffic on the hidden service. And we see if the clock skew adapts accordingly. And then we take the traffic away again. And then we see if the clock skew adapts again. So basically, we are creating a more active CPU with lots of traffic, so the clock will heat up, and that's what changes the clock skew, for those that couldn't follow. How can we solve this? We could create dummy traffic, just to keep it equally hot. Every server administrator will tell you, no, we're not going to do that. We could use a fixed quality of service for all connections, which then basically says no anonymous stream should affect another. Problem, you have a potential DOS in there, because you could use up all the connections, and the connections would be idle. And also, even if you have like constant ones, idle connections don't have the same CPU load, so the heat will be different, so there will be a clock skew difference, so that won't really work. Another option would be often-controlled crystal oscillators. That would be a hardware solution, and I think it sounds as one of the best solutions that I've heard of. The reason it's not being put into place so far is, I think, solely the price. And we could also always run the CPU at maximum load, which, of course, again, nobody will accept that in real life as a solution. This is academic, but not applicable. So, 9 years later, revealing hidden services this way is still possible. And I think in a world where we have to rely more and more on Tor and ways to hide stuff, especially for dissidents and everything, this is a highly critical one. So basically, possible targets are users. We can track them. Servers in multiple ways. And back then, when those papers were written, most of the Internet of Things devices weren't in there, but it also goes for all of these. The patch level is kind of interesting on those too. If the firmware wasn't upgraded and we know there's a publicly available exploit, or we have a 0-day, we can create an easy botnet with all the IoT things. So unless, of course, they're running on UDP. Who would have thought that UDP saves your ass? So in conclusion, more or less everything is affected by TCP timestamps and their ways of exploiting. The air show is right above us. So, let's get to some new attacks. These are some attacks I've stumbled across or developed. So one is revealing active-active load balancing. Basically, the way to identify it is super simple. I don't know why it hasn't been published before, but there you go. It's if you have multiple timestamps on one port, and you know it's not the same, either somebody got this really stupid idea of randomizing timestamps, which is not going to be the case. I'm 90.9% sure this is like. But the way higher chance is that there's a load balancer and there's actually multiple machines answering. I hope this graph will show properly. This is, oh, I wish this laser thingy would work. Does it? Can I just not? Too bad to aim. All right. Well, so this is Microsoft.com, and we're reading timestamps. This is an HPing command. This is the output of an HPing3 command. I didn't write a POC script because it was too simple to see. There, you see the system uptime seems 331 days, 5 hours, something. The next one is 33 days, 2 hours, something. The next one is 331 days. So this could be an indicator for load balancing. In this case, it's not. You see also there is, in the line of the 33 days, 2 hours, if you go up 3 lines, it says dup. And if you look at the actual TCP timestamps, which is the line below, it says TCP timestamp, double point, TCP TS. If you look at those, they're sequential from the first one to the next one to the one after. But on the very last one, I really wish the pointer would work. Well, there's one that says 28619, and the one on the very bottom says 280. And this far up high in the numbers, this is a completely different system answering. So there we've spotted load balancing, active load balancing. As easy as that. Then another attack I've developed was network layout information gathering. And there's a 2007 in there, and I'm going to get to it in a second. But first, let me show you what happens. So I have to get the VM out. And Windows died, as it usually likes to do. Or we would like it to do. So let me launch that quickly. Just take a sec. All right, so what we're going to do is a very straightforward, simple network scan. And just so we have no confusion, what we're doing here, I hope it's not new, but it's a SYN scan over all ports, super fast, very verbose, OS system detection. That's just the IP of the system that's facing externally, and we're going to write the results as XML files just so we have it for later things. And that takes a bit, but everybody knows what's happening, right? Any questions while we're waiting for it to be finished? So we see it's discovered port 22, 80, and 443. And another port. few more seconds, and we're going to be done. We have the time. Totally fine. All right. So the interesting part now is the following. We're going to run Python and identify host scripts on the test scan. Test. There you go. Oh. Okay. I'm very sorry about that. This is not a problem. This is a feature. I knew this was going to happen, and so I practiced, because it's really difficult to put one line after another. Oh, it did work anyway. Ha! Ha ha! I didn't see that. No. So basically what you're seeing now is it discovered different hosts and which port it was, and it, in parentheses, wrote with what the timestamp was. So this is nice. This is way easier than working with Skew, I tell you, because the Skew people never released their source code anywhere, so have fun calculating Skew. But TCP timestamps are super easy to read. We showed it in the beginning. So everybody can do layered information gathering on the basis of TCP timestamps. So I have to switch back. That's okay, we're going to switch out in a second anyway again. So basically what you saw was there was different timestamps on different ports. We grouped those together. We know what the ports were. Actually, this bothers me, so I'm going to do it anyway. Ha! Again, very good. So 2007, we've mentioned this before. 2007, so I've counted this as a new attack. Theoretically, this is an old attack, but it's never been an attack. So actually, a friend of mine showed me this paper after I was like, hey, look what I can do. And he was like, it's been done before. I was like, really? And he's like, yeah. And I searched for it, I couldn't find it. And the reason I couldn't find this is because none of it in that paper is offensive. There is no offensive security in it whatsoever. What they did, it was a streaming server. Streaming, I think it was video streaming. And they had lots and lots of requests from one IP address, and they were like, what's happening? And with TCP timestamps, they could figure out that on the incoming side, they were the receiving side, so they weren't attacking anybody. They were just receiving it, and they were like, oh, there's different timestamps, so there's different machines, so it's just a student network or whatever that all have the same outgoing IP address. What we did now is we identify hosts behind the NAT system that we want to attack. So that is, I think, quite a difference. If TCP timestamps are the same, services are on the same host. If TCP timestamps are different, services are hosted on different hosts. If some ports answer with no timestamp, well, we don't know. We just can't tell. There is, again, no tool to exploit this. The identify host scripts that you just saw, that one is on GitHub. It's not very pretty code necessarily, but you can feel free to use it anywhere you want to. You can improve it. I would really encourage those that want to play with Nmap to write Nmap scripts and put the load balancing check and also the network layout information gathering either as a script or directly in. This would be really nice. Anybody? No? Just think about it. Maybe one of you will be like, oh yeah, I want to do this. And I'll be happy for it. So ways to defeat against it, you could increment randomly, but then it defeats the whole round-trip time measurement, and also it would break the RFC. We could rewrite the timestamp on a NAT device. That would actually work for both my attacks. So yeah, keep that in mind. But yeah, so we could also use it in a different way. We could improve the OS fingerprints of NAT devices. What's a fingerprint? OS fingerprint is like a human fingerprint, but for operating systems. Ta-da. And Nmap doesn't assume the aforementioned scenario. So Nmap always thinks your port's getting it directly. And this is not the case if you're pen testing from the internet nowadays anymore. So we use the knowledge which ports belong together, and we don't use closed ports. Even if Nmap tells you to, don't do it. Okay? Because the closed ports are not the device we want to interact with. So again, we're switching to our VM. There you go. So we're going to do port scans again. They're not going to take this long, I promise. But before we're going to do port scans, I want to show you the OS fingerprint that Nmap thinks of this device. Oh, come on. Does it show somewhere? Oh, there we go. Fingerprint. No, that was the TCP fingerprint. This is because of the zoom. We want you to see something. There you go. Aggressive OS fingerprint. It's a Linux 3.2 or 3.8, somewhere in there. That's what Nmap tells you. So now we're going to just scan port 22 and port 8082, because we know those belong together. And wait. It's doing the OS detection, and we have to scroll up again. Aggressive OS fingerprint, it's still the same. Well, maybe it wasn't that exact after all, that bad. Let's try the other one. So those were port 80 and 443. Scroll up there. Oh wait, look at that. It's a completely different server. We could OS fingerprint way better than Nmap did it before, just by saying we only want the ports that belong to the host, actually, to the same host. Might kind of make sense if you put multiple fingerprints of people over each other, try to detect which person it was. So that's new. Proposed solutions, we could terminate at the firewall. And somebody asked me if we could use reverse proxies to do so. Reverse proxies might work if the TCP timestamp isn't copied. So since I haven't looked at any reverse proxies in this respect, I can't tell you if it's a solution or not. But if you would terminate it at the firewall and you start a new connection outbound and you don't use the same TCP timestamp, the solution will work against my attacks. Have fun implementing it. Would be cool. But generally, I want to ask, why haven't we fixed this? And Kono et al., that's the guys that released the 2005 Clock Skew paper. It's the first one in this field. It's the one that marked the biggest impact. It says it's possible to extract security-relevant signals from data canonically considered to be noise. So basically, it's that there's other ways to gather the same intelligence excuse. I don't think that's an excuse that holds up, but it could be one of the reasons why we haven't fixed this. It might not be considered important. I don't know how tracking users through the internet in days like now is not considered an issue. And maybe the biggest one why we haven't solved this, and you've seen it, there's just not that many good solutions out there. There's more timestamps, and they have their own set of problems. An ICP timestamp has a CVE attached to it. A TLS timestamp has a Tor bug attached to it. The HTTP timestamp has an interesting other paper. And the biggest difference between TCP timestamps and all these timestamps are that TCP timestamps don't get reset to 0 or synced. So the vast majority of timestamps gets synced together with a real clock. So the clock skew isn't that big, and the off is not that big. ICMP timestamps get reset to 0 every day, so we cannot do the uptime calculation on them. So, but it's just some more timestamps you can do research on. Then I just wanted to put like the summary of the presented attacks together. We had uptime calculation, which is more than 10 years ago. Then we had host identification, which is 10 years ago. Then network layout information gathering. This is what we just looked at. Then revealing active-active load balancing, improving OS fingerprints on netted devices. And in the clock skew department, we had host identification, user tracking. We had network layout information gathering, and revealing hidden services. So what now? Good solutions, suggestions are welcome. Before we get to them, I wanted to point you to the papers some of the papers at least that I've read for this to get where I am, and more papers. And I would all like to thank you very much for listening to my talk. And if in the question and answers you have suggestions, I'd be very happy. Thank you very much.
Hi. So thank you very much for the talk. I was wondering, you talked about the possibility to retrieve a unique ID from this clock skew. Do you know how many samples you require for this? How unique is it? Or
no, I don't. I haven't measured clock skew myself on any of the devices. I've read about them because I was exploiting the simpler version. But the second paper up there is very likely the best way to find out.
All right, thank you very much.
Hello. I wonder, what if we reset periodically the clock with a value initiated by a time server?
You want to reset it to where? Reset it to 0, or you want to also sync it? Is it?
The 0 value will be the Unix timestamp.
Mm-hmm.
So every host will have the same initial value of one server, a time server.
I think that has been discussed too, and I think they figured out it's just too darn tricky to do because it's implemented through, at least in Linux, it's implemented through Jiffies. And syncing Jiffies across the network is kind of nasty. And there was another reason why it was turned down, that idea. I don't recall one of those papers. But the solution had been proposed and it had been flagged not usable. But this is one way of
Okay, thanks.
yeah. But keep them coming. I mean, I don't want to discourage you being like, that doesn't work, but maybe one of you has one, yeah?
Hello.
Hello?
You said that the clock skew was affected by the heat of the processor.
It's affected by the heat, yes.
Yes. Can we imagine that randomizing the cooling system could be a good way to affect or to mitigate this kind of...
Randomizing what?
The cooling system behavior.
I'm sorry, I don't understand it.
The cooling system behavior.
The cooling system behavior.
Cooling.
Somebody help me out. Interesting one. Yeah, that sounds interesting. I guess we should try out. I haven't seen that one proposed anywhere. Nice one.
Thank you.
That was against clock skew attacks, not about the plain, simple, straightforward TCP timestamp attacks.
I'm sorry, this is still another question about time skewing. Isn't there any issues with SMP CPU? Because I don't know for real-time clocks, but the timer interrupts are per CPU related. So nowadays, every server has a lot of cores or even a lot of CPUs. So isn't there any jitter or differences, whether you are scheduled on one core or the other for a VM? So don't you lose any precision in the measurement of this phenomena?
That's an interesting one too.
Sorry.
No, don't be sorry. I think it's very interesting. So just let me clarify if I got that right. So you're saying, does having multiple CPUs mess with clock skew? Okay. I will ask Kono. I'll write him a mail. I'll be like, hey, you don't know me, but yeah. It sounds interesting. I have no idea if they have problems with it. The vast majority of the tracking and the exploiting of clock skew is less of a penetration tester tool. It's not something I would use on a daily basis. For one, there's no tool out there. Second, I'm too lazy to write it myself, especially since I can do it with simple TCP timestamps and all the bigger things that you can do with clock skew. That is out of my hands because I don't have access to the backbones and stuff. As secret services would have. But it is I hope they are having problems with it. Yes, I do. That's interesting. Fan, multiple CPU cores, yeah? Well, if there's no more questions or suggestions, I thank you very much and I wish you a lovely coffee break.